In this video, we're going to be looking at the double angle formulae. But to start with, we're going to start from the addition formulae. Not all of them, but just the ones that deal with A plus B. So let's just write those down to begin with. Sine of A plus B, we know, is sine A cos B plus cos A sine B. Next, we want the cos of A plus B, which will be cos A cos B minus sine A sine B. And finally the tan one, tan of A plus B, which will be tan A plus tan B over 1 minus tan A tan B. So those are three of our addition formulae, and each one is to do with A plus B. So, what happens if we let A be equal to B? In other words, instead of having A plus B, we have A plus A. So that would be sine of A plus A would be sine 2A. And what does that do to this right-hand side? Well, it gives us sine A cos A plus cos A sine A. In other words, these two are the same, so we can just add them together. So sine of 2A is 2 sine A cos A. And that's our first double angle formula. Double angle because it's 2A. We're doubling the angle. So what is its sine, and so on. Let's do the same with cos. Let's put A equal to B. So we'll have cos 2A is equal to, well, it was cos A cos B. It's now going to be cos A cos A, which is cos squared A. Sine A sine B, well, it's now going to be sine A sine A, which is sine squared, minus sine squared A. And that's our second double angle formula. Doing the same with tan. Tan 2A is equal to tan A plus tan B. This is now angle A. So it's tan A plus tan A, which is 2 tan A. All over 1 minus tan A tan B. But this is now A instead of B, so it's tan A. Tan A times by tan A is tan squared. 1 minus tan squared A. And here are our three double angle formulae. Again, to be learned, to be recognised, and to be used. Let's just have a look at this one. Cos 2A. Why pick out this one? Well, it's this right-hand side which is the bit that interests, because it's got cos squared and sine squared in it. And there is an identity that's to do with cos squared plus sine squared equals 1. What that means is we can replace the sine squared and get everything in terms of cos squared, or we can do it the other way round. So let's just have a look at that one. Cos 2A is cos squared A minus sine squared A. But cos squared A plus sine squared A equals 1. In other words, sine squared A is 1 minus cos squared A. So we can replace the sine squared here in our double angle formula by 1 minus cos squared. So we'll have cos 2A is cos squared A minus 1 minus cos squared A. Using the brackets, notice, to show I'm taking away all of it. And now let's remove the brackets. Minus 1 minus minus gives me a plus cos squared A. And so I now have 2 cos squared A minus 1. So that's another double angle formula for cos 2A. Now, because I replaced the sine squared here by 1 minus cos squared, I can do the same again and replace the cos squared by 1 minus sine squared. And what that will give me is cos 2A is 1 minus 2 sine squared A. So, a lot of formulae there. Let's just write them all down again. Sine 2A is 2 sine A cos A. Cos 2A is cos squared A minus sine squared A, and we can rewrite that as 2 cos squared A minus 1, or as 1 minus 2 sine squared A. And then tan 2A is equal to 2 tan A over 1 minus tan squared A. So there are our double angle formulae. Formulae to be learned, formulae to be remembered, and most importantly, recognised and used when we need them. So, let's have a look at how we can make use of these double angle formulae. So, sine of 3x. Is it possible to write sine of 3x all in terms of sine x? Well, let's try and break this 3x up. 3x is 2x plus x, so we can write this as sine of 2x plus x. Okay, this means we can use our addition formula. Sine of 2x cos x plus cos of 2x sine x. Now I can use my double angle formula here. Sine of 2x is 2 sine x cos x, still to be multiplied by cos x, plus. Now I have a choice. There are 3 double angle formulae for cos 2x. So my choice has got to be governed by what it is I'm trying to do. And we're trying to write sine 3x all in terms of sine x. That means the choice I have to make here is the one that's got sines in it. Not cosines, but the one that's got sines and only sines. And the one that has that is 1 minus 2 sine squared x, still to be times by sine x. So, this front term is going to be 2 sine x cos squared x. 1 times by sine x is plus sine x, minus, and 2 sine squared x times by a sine x is sine cubed x. Well, we're getting there. We've got sine here, sine cubed here, cos squared here. But cos squared can be rewritten using one of the fundamental identities. Cos squared plus sine squared is 1. So cos squared can be replaced by 1 minus sine squared. And so we can see here everything is now in terms of sine x, and all we need to do is tidy it up. So we multiply out this bracket, 2 sine x for the first term, 2 sine x times by 1. Then we have 2 sine x times by minus sine squared, minus 2 sine cubed x, plus sine x minus 2 sine cubed x. 2 sine x plus sine x, that's 3 sine x, minus 2 sine cubed minus 2 sine cubed is minus 4 sine cubed x. And there everything is in terms of sine x. You can do the same with cos as well. Cos 3x can be turned into an expression that's entirely in terms of cos x. That's an example of using our double angle formulae in order to reduce, if we like, to use that expression, a multiple angle, sine 3x is a multiple angle, down to a single angle in terms of the sine of that angle. Let's have a look now at solving an equation. Let's take cos 2x is equal to sine x. And let's take a range of values for x, which puts x between plus and minus pi. Again, I've deliberately chosen cos 2x because we have a choice. We have 3 possibilities. Which one do we choose? Well, if I want to solve an equation like this, I really need it all in terms of one trig function. Not 2, but 1. And here I've got sine x. It therefore makes sense here to replace this by 1 minus 2 sine squared x equals sine x. Now we have a quadratic equation where the variable is sine x. Let's rearrange that so that it equals 0. Add the 2 sine squared to each side, plus the sine x, and take 1 away from each side. This is now a quadratic equation. Can I factorize it? Let's have a look. 2 brackets, 2 sine x and sine x. When multiplied together, these two will give me the 2 sine squared. I need minus 1, so let's pop a 1 into each bracket. And one of them's got to be plus and one minus. I need plus sine x in the middle. So I'm going to make this one plus 1, so I get plus 2 sine x. Make that one minus, so I get minus sine x. And when I combine those two terms, plus sine x there. This says a bracket, a lump of algebra times by another bracket, another lump of algebra, is equal to 0. And so one or both of these brackets must be equal to 0. and so we've reduced this fairly complicated looking equation down to two simpler ones. And this one tells us here that sine x is equal to, add 1 to each side and divide by 2. Sine x is a half. Or this one here tells us that sine x is equal to minus 1. We've now got to extract the values of x from this information, and those values of x must be between plus and minus pi. So let's sketch the graph of sine x between plus and minus pi. And there's the graph. There's pi, pi by 2, minus pi by 2, and minus pi. And it goes between 1 and minus 1. So let's take this one first. Sine x is minus 1. Well, that goes across there and down to there. So x is minus pi by 2 is one answer that we get there. Sine x is a half. A half goes across there, and we should recognise that this is one of those nice numbers, sine x is a half, for which we've got an exact answer. And so what we do know is that the sine of 30 degrees is a half, but we're working in radians. So in fact, 30 degrees is the same angle as pi by 6. And this is symmetrical, remember, the curve for sine is symmetrical. So if that's pi by 6 in there, that's got to be pi by 6 in there. So this, in other words, will be 5 pi by 6. And so we have our two answers for this one, pi by 6 and 5 pi by 6. So there we see that we've been able to solve our equation using our double angle formula. And by making the right choice, particularly here, when with cos 2x, we know that we have three possibilities. So, let us have a look at another equation, again using our double angle formula. Sine 2x equals sine x. And again, let's take our value of x to lie between plus and minus pi. We've only one choice for sine 2x. That's 2 sine x cos x equals sine x. Now, it's very, very tempting to say, common factor on each side, cancel it out. And then we've lost it. And because we lose it, we might lose solutions to the equation. So what's better than cancelling out is to get everything to one side by taking sine x away from each side and then take out a common factor. And here there's a common factor of sine x, which will leave us 2 cos x minus 1. Two expressions multiplied together give us 0. So either or both of these expressions is equal to 0. So either sine x equals 0 or 2 cos x minus 1 equals 0. Now, we've managed to reduce this equation to two smaller, simpler equations. One's for sine and the other one's for cos. But each is going to give us a value of x. Let's take this one first. Sine of x is 0. And let's draw a sketch up here of sine of x. There it is. And it's 0 here, here, and here on the x-axis. At minus pi, 0, and pi. So straight away we've got x equals minus pi and 0. Not pi, because pi is excluded from the range that we've got. But notice, sine x equals 0 gave us 2 answers for x. If we'd have cancelled sine x out up here and just got rid of it, we would not have got those 2 answers. Let's go to this equation now. 2 cos x minus 1 is 0. So that tells us that cos x is equal to a half. And what we need to do is sketch the graph of cosine. And the graph of cosine looks like that, between pi and minus pi. And here is the half. And cos x equals a half. This is another one of these nice relationships. And we know that this one is 60 degrees, or, because we're working in radians, pi by 3. And because of symmetry, this one here has got to be minus pi by 3. And so x is minus pi by 3, or pi by 3. And so we've got our 4 solutions for this equation. In doing this work with double angles, in effect we've been looking at what are called multiple angles. And here I've been drawing sketches of a single angle, if you like, just sine x, cos x. So the question is, what does the graph of sine 2x look like? What does the graph of cos 3x look like? Or for that matter, what about sine of a half x? Well, let's just explore that. Sine x. Let's just have a look at its graph between 0 and 2 pi. So that's sine x. Now what about sine 2x over the same range? Well, let's just think about it. What are we doing when we're multiplying by 2? Well, we're doubling, yes. But what that means is everything that happens on this graph happens twice as fast on this graph. So in the time it takes this to go from 0 to 2 pi, it's done all of that in this space. So that bit of graph appears in this space, so that we have up and down and there. And then, of course, it's periodic, so it does it again. So sine of 2x gets through everything twice as quickly as sine x. And sine of 3x will get through it 3 times as quickly. So I'll have 3 copies of this graph in the same space 0 to 2 pi. And the same with cos 2x and cos 3x and cos 4x. What if I take sine of a half of x? Well, let's do that. Sine of a half of x. I'll do sine of x first, just to give us the picture again. That's our graph between 0 and 2 pi. So what about sine of half of x on the same scale? Well, things are happening half as quickly. A half of 2 pi is just pi. So we will only have got through that bit of the curve by the time we've got to 2 pi. So that in effect the graph of sine a half pi looks like that and continues on in double the space. So graphs of multiple angles look a little bit different to the ordinary angle. But the thing that we have to remember is that if we have a multiple here that's greater than 1, then it's going to get through it much quicker, and we're going to see the graph repeated. If we've got a multiple here that's less than 1, it's going to take longer to get through the graph, and we're going to see the graph extended and drawn out. Let's have a look at the graph of cos x and cos 2x. Again, between 0 and 2 pi. So there's our graph. What about mark the points in the same positions? This is going to go through twice as quickly, so we're going to see that shape repeated in this space here. So we're going to see that come down and go up, and then we're going to see it repeated again, like that. So sketching these graphs at multiple angles is quite easy. All that you need to do is look at the original graph and judge the number of times that it's going to be repeated over the given range.